All right, so this is the extra examples that we were looking at from section 6A.2. This doesn't finish 6A.2, but it is some of the extra ones that we wanted to get done before our next class. So it says Sally has a mass of 80 kilograms and Dave weighs 190 pounds. What is Sally's weight as a percentage of Dave's weight? So notice we're asking, we're wanting to put Sally's weight as a percentage. So what portion out of Dave's weight is it? So Sally's weight divided by Dave's weight as a percent. That's the goal. The problem is that they're in different measurements right now. So we either want to convert Sally's kilograms to pounds or we want to convert Dave's pounds to kilograms. We need to go one of the two ways so that they'll both be in the same units of measurement. So if we do the 80 kilograms, let's say we start with Sally over 1. And we want to change kilograms to pounds. Notice this is different than the one on the formula sheet. That's why I said sometimes you just want to use what they give you in Newton. So 2.205 over 1. So we're going to multiply that 80. So let me make sure I'm sharing my screen with my calculator. Times the 2.205. That's 176.4 pounds. So now we can truly more easily compare their weights together. So if we put Sally's weight, which is then 176.4 pounds over 190 pounds, notice these are both in pounds, we can divide that and we can figure out what that percentage would be. So that would be nearest whole percent. So that's going to be, that would be 92.8%. So that's going to be 93%. So Sally's weight is 93% of Dave's weight. Now, we could have just as easily have converted the 190 pounds to kilograms. We would have ended up dividing because we would have had pounds on the bottom and kilograms on top. I'm not going to write this one all the way out. Just wanted to show you the difference. And that would have been a little trickier because we would have had this long, nasty decimal point for Dave's weight. So we probably would have taken that out to at least 4 decimal places. So Sally was 80 divided by the 86.1678, just to make sure we don't cut it off too soon. And notice we do get about 93% again. So you could have done it either direction. It just worked out a little bit cleaner and a little bit nicer this direction without the long decimal. So let's look at number 9. It says, while shopping in France, Johnny notices that the cost of apples is 3.40 pounds per kilogram, or euros, sorry, euros per kilogram. Johnny isn't familiar with euros or kilograms, but he needs to convert the unit price into dollars per pound because that's what he's used to. He knows the following things. The conversion rate from dollars to euros is $1 is 88 euros as cents. Notice 0.88 euros. And there are 2.2 pounds to a kilogram. So let's look at what we have. So he was dealing with, and I don't have a fancy key on my typer for all of that for the math formulas. So I typed my euro as a capital E. But 3.40 euros over 1, since it's not stated, kilogram. We're going to first convert that to pounds. So notice the kilograms need to be on top, so that'll cancel. So 1 kilogram is 2.2 pounds. So that's going to cancel out my kilograms, and I'll be in pounds on the bottom. My money I wanted was supposed to be dollars. So we need to convert euros to dollars. So here they gave us the conversion for that. The 0.88 euros is equal to $1. So notice this cancels out the euro and we have dollars per pound. So if we're working this one out, we're going to be, you can do, remember, one of two things. You can work from left to right. I'll show you that. So you can do 3.4 divided by the 2.2 because that next number's on the bottom. Hit enter. Don't clear anything. Divide by 0.88. Hit enter again. And we want to round this to the nearest cent according to the directions. So that'd be $1.76 per pound. Okay. I could have also gotten that by multiplying the two bottom numbers together and writing that down, which is 1.936, and doing 3.4 because it was times a bunch of ones divided by 1.936. So all my top numbers multiplied divided by all my bottom numbers multiplied. So either way, we get $1.76 per pound. Okay, a wildfire has spread and engulfed 59 acres of dense forest. If there are 2 trees for every square meter of forest, how many trees were consumed in the fire? So the first problem is we know the acreage of the forest. We don't actually know how many square meters we have in the forest. Once we figure that out, we know that we're going to lose 2 trees for every square meter. So it looks like the first thing they gave us is they're about 3.281 feet per meter and 43,560 square feet in an acre. And we want to round our answer to the nearest 1,000 trees. Okay, so let's look at this. So I have 59 acres in the forest over 1. I know that an acre, which I want to cancel out, 1 acre is 43,560. Notice this is feet squared. That's going to be really important for this next part because this is in feet squared. This other conversion they gave us is in feet per meter. No square feet, no square meter. It is just singular foot and singular meter. So when we are doing this conversion, we are going to put feet down here to cancel out the foot, but that only cancels out one of those feet squared. So this is called a double conversion, where we're trying to get rid of square units, and we have to do that by doing the same conversion fraction twice. So if I put that same fraction down again, notice that will give me 2 feet to cancel with the feet squared. So I'm going to kind of do some color coding here. The acres canceled here. The foot squared cancels with these 2 feet, because there's 2 of them to cancel that group of 2, because feet squared means feet times feet. Notice now I have 2 meters on top. So when I multiply, I'm going to get meters squared. So that's going to be important for our final answer. And then what we had, our last little step was we wanted to know that there were 2 trees for every square meter. So meter squared is going in the bottom because the other 2 meters are on top. And we're talking about the number of trees per square meter. So there was 1 square meter, since they didn't state the number. Every one of those is 2 trees. So notice again, this is kind of a double conversion cancellation. It took 2 of these to match this. So that way we could cancel it out. Okay. So now what we're going to get is the total number of trees on our top. And we just have 1, no unit in the bottom, just all of our multiplication. So let's work out the multiplication on this one. So I'm going to do the top all the way across. So 59 times 43,560 times 2. We're going to write that down. That's 5,140,080. We're going to be dividing that by the 3.218 or 81 times itself, 3.281. There were 2 of those in the denominator. That's dividing by 10.764961. So 5140080. Oops, got too many zeros in there. 5140080. There we go. 5,140,080 on top, divided by 10.764961. And we're rounding. Be very careful. I highlighted this for you on purpose. I'm going to write my answer out and then we're going to round it. So 477,482.454, and it goes on forever. We're not going to be rounding in the decimal point anyways. We're going to be rounding in the thousand place, not the thousandth place. So the thousand place, remember, is in the whole numbers. So right here, this is in the thousand place, and behind that is a 4, so that's not going to bump up. So we would round that to 477,000 trees would have been lost. Okay. All right, let's look at our last 2 on this little video. It says a bridge is rated to a 100-ton capacity. What is the maximum weight object that the bridge can support in kilograms? Round to the nearest whole number and do not include units or commas in your answer. So that's a Newton note. Sometimes you can't put your commas in. They want whole, just type in your digits. Note that there are 0.454 kilograms in a pound and 2,240 pounds in a ton. Note, this question is using a British ton, which is not as the same as a U.S. customary ton. Always use any conversions given in the problem for that specific reason, because there are 2 types of ton, but this one is specifically the British ton. So We're starting with 100-ton capacity. We're going to cancel tons out and change it to pounds. So 1 ton is 2,240 pounds. Okay. We want to change pounds to kilograms because the question was, what's the maximum weight the object can support in kilograms? So pounds to kilograms, we have a connection there. It was 0.454 kilograms is 1 pound. So my tons are canceling, my pounds are canceling, everything's on top, so we're just multiplying. So 100 times 2,240 times 0.454. This would be 101. They said no commas, 696. So if you were typing that in Newton, you would want to type it in just like that. And usually they would have the kilogram out to the side. They don't usually make you type in the units. So, and they didn't give us any rounding. Oh, yeah, nearest whole number, which is fine. We're already a whole number. Okay, so let's look at this last one because we're going to pick up with the area ones in class next time. So if Mars travels at 24,126 meters per second in orbit around the sun and takes 1.88 Earth years to complete its orbit, what is the total distance in miles that Mars travels throughout its orbit? Round our answer to the nearest whole. Do not include units or commas in our answer. There are 1,609 meters in a mile. So let's start with what we have. 24,126 meters per second. That's 1 second. And it takes 1.88 Earth years to complete its orbit. What's that total distance in miles? So we're looking at a singular moment in time. We're also going to have to convert that to a whole Earth, to how many Earth years that is. We're going to have to make sure we do a conversion with that because it's right now in seconds. So let's talk about this one. So let's first convert our meters to miles. So we want the meters to cancel and the miles to be part of our journey. So that's 1,609 meters is 1 mile. Okay, so now we're in miles, but that would be total miles per 1 second right now. So we want to know what is going to be the total distance in miles it travels throughout its complete orbit. So we're going to have to convert to Earth years and then use this fact that it takes 1.88 Earth years to complete its orbit. So to get to Earth years, we have to get to how many days there are probably in a year. So we know that we can turn seconds, which is on bottom right now. So actually I'm going to change colors. Seconds is on the bottom. So we're going to convert that by putting it on top, and we're going to convert it to minutes because that's the easiest jump. So there are 60 seconds in 1 minute. Okay, so now we have the total miles traveled in a minute. Now we're going to convert minutes to hours. And those minutes are going to cancel, so there's 60 minutes in 1 hour. So right now we would be total number of miles that Mars traveled in an hour. Then we're going to convert that to days. So we have hours on top, days on bottom. There are 24 hours in a single day. Okay, so we're getting close. Now we want to figure out how many days are in a year because we're talking about an Earth year. So there are days on top, so it'll cancel with days on the bottom. It's going to be, I'm going to write Earth year since they want to be specific about that. There are 365 days in a standard Earth year. Okay, now we're not quite done because this just tells us how far did Mars travel in a single Earth year. They actually have, it takes 1.88 Earth years to do that. So we're going to have that last little fraction. It's actually going to get rid of all of our time units unless you know to write this on the bottom. This would be 1 Mars orbit. We can write that, okay? So the Earth year is being converted to Mars orbit time. How long does it take it to go around its whole orbit? Okay, so that's a lot of fractions there. So we're going to multiply and divide as we go from left to right, just so we don't have to remember a bunch of decimal points. So 24,126. The second fraction is dividing by 1,609. Hit enter. The third fraction, the 60 is on top, so times by 60. Hit enter. The fourth fraction, the 60 is on top, so we times by 60. The fifth fraction, the 24 is on top, so we times by 24. The sixth fraction, the 365, is on top, so we times by 365. And then the last one, it is times the 1.88. So this would be 88.8. Sorry, I'm trying to read and write 983. I'm going to remind you not to put the commas in. I'm just doing it so I can verify this. 572, they said nearest whole number. So this would be miles. So when you type this into Newton, remember, don't put the commas in there since they specifically said not to. But that is 888,983,572 miles to complete the entire orbit. Okay, so that ends this little video. We will finish everything else from section 6A.2. I believe that's the right section. We will finish that up in class together. And then we'll be moving on to 6A.3 and then to the 6B material. All right, hope this helps.